In this CHI 2020 paper, I'm going to present our work on the next generation of human-drone partnerships, co-designing an emergency response system. The work was primarily conducted at the University of Notre Dame in collaboration with the firefighters at the City of South Bend and our collaborator at Johannes Kepler University. Advances in technology mean that drones are increasingly used in society to support diverse tasks such as emergency response. For example, they can be used by firefighters to create thermal maps of burning buildings, to map out hotspots, or to search for victims in windows. They could also be used for search and rescue. Here we show live imagery from a demo we conducted in the spring of 2018 with the South Bend firefighters. Multiple drones autonomously flew search routes over the river while firefighters conducted a training exercise. In this example, 2 of our undergraduate students created a drone-based system for dispatching defibrillator devices. In fact, drones are already used by emergency responders. However, in current practice, they tend to be manually operated by a remote pilot. The fire at Notre Dame Cathedral was a highly visible example of this, where drones were used to capture a bird's eye view of a fire. In contrast, our vision is for drones to serve as intelligent partners in emergency response, making autonomous decisions as fully fledged members of the emergency response team. In addition to autonomy, drones need the ability to collaborate with other drones to achieve mission objectives, and they need to interact with humans as team members. We're building our solution over our existing dronology platform, which supports the coordinated flight of multiple drones. In this mock-up of a river rescue scenario, drones have been dispatched to search the river. They plan their own routes, use onboard image detection, and when a victim is sighted, they dynamically switch to tracking mode and notify human responders. Part of this challenge is detecting victims with high degrees of confidence, even though they might be partially submerged, or the weather conditions might provide low visibility. Drone response is an example of a complex socio-technical cyber-physical system in which multiple humans are interacting with multiple drones. As such, designing the drone response user interface represents what we call a wicked design problem. These kinds of problems are characterized by the fact that they represent unique domains with no well-formulated solutions. There are multiple stakeholders, often with conflicting needs. There's no definitive known test of a solution's validity, and there's little opportunity to learn by trial and error. To design a solution in this space, we worked very closely with the firefighters in the City of South Bend. We created visionary mock-ups of some of the scenarios that the firefighters had told us they were interested in. On the left, you can see a very early mock-up of what it might be like to use UAVs to support structural fires. And on the right-hand side, you can see a scenario for using multiple semi-autonomous UAVs in a river rescue scenario. The firefighters were already using manually flown UAVs to support several different emergency scenarios, and we wanted to know what they liked and didn't like about their current system. So we conducted a series of interviews, and as part of those interviews, we asked them to create a mock-up of what they would like the drone response UI to look like. One of the things we discovered through this early design process was that we needed a way to help the firefighters think about what would be different about drone response. Whereas in their current usage scenarios, they were manually operating the UAVs. In the future drone response scenario, the UAVs would be semi-autonomous, and the ways that the firefighters would interact with them would be quite different. This led to the primary focus of this paper, which was on situational awareness. We wanted to design a system that would help the firefighters to fully understand what was happening in the current mission and what each of the drones were doing. So situational awareness is defined as the ability for users to fully perceive understand, and make decisions in a given situation. And there are 3 levels of situational awareness. Perception is all to do with recognizing and monitoring what is going on in the environment. Comprehension is about interpreting that information and synthesizing it, while the final level of projection is about understanding the dynamics of the environment and having the ability to project future states so that you can make decisions about what should happen next. There are 8 common design errors that occur frequently in user interface designs which inhibit situational awareness. These have been documented as situational demons by Micah Ensley. Examples of these are attention tunneling, out-of-the-loop syndrome, errant mental models, when a user thinks they understand what's happening, but they in fact have an incorrect conceptual model of the scene, requisite memory trap, misplaced salience, and information overload. We also identified 3 new demons associated with socio-technical cyber-physical systems. The first one, enigmatic autonomy, occurs because robots and other agents are able to operate autonomously. However, their current permissions and capabilities may be unclear to the users. The second situational awareness demon occurs because socio-technical cyber-physical systems require a significant amount of communication between both humans and machines. When communication failures occur, important information that should be known by all of the different agents, humans and machine, may be missed, and this can cause all sorts of problems. Finally, the problem of misaligned interfaces. Misaligned interfaces occur when there are inconsistencies between the information portrayed in a graphical user interface and a physical interface. When drones are flying in drone response, the user interface shows that they are in flight mode, and the positioning of switches on the handheld controller is entirely ignored. In this instance, the user decided to take control back from drone response and to manually control the drone, but they failed to notice that their throttle, shown with the red arrow, was in the fully downward position. As a result of the misaligned interfaces, the drone plummeted to the ground and met its demise as shown on the left-hand side of this screen. Our goal was to work closely with the firefighters, to collaborate with them in order to design a solution that would provide them with full situational awareness throughout a mission. We used a scenario-driven approach. First of all, based on the brainstorming and interview meetings that we previously held, we documented a set of use cases which described what a mission would look like. Here you can see an example on the left-hand side. And then based on that use case, we extracted specific scenarios. These scenarios were designed to probe some of the situational awareness demons. Examples included victim identification, for example, when a drone would search for a victim in the river, find the victim, and then autonomously switch to tracking mode. Lost communication when the drone would fly out of the search area and communication was lost. Battery replacement when a UAV with low battery autonomously returned home. Manual takeover, which we've discussed, and the situation when many different events occurred simultaneously and multiple alarms were sounded. We then created an executable prototype which had the capability of enacting each of those 5 scenarios, and we used this enactment to support a series of user studies. The participatory design process involved 3 different design sessions. In the first session, we explored some exploratory ideas. In the second session, we explored with 2 different firefighters the specific situational awareness demons that I've been discussing. And then finally, in our final session, we met with 8 members of the fire department and we walked carefully through each of the different scenarios and collected a lot of different feedback and ideas for integrating into the final design. In each of these studies, we focused on the 5 different use case scenarios. For each one of them, we enacted them in the executable prototype and focused on questions associated with perception and comprehension. What do you think is happening right now? Projection. What would you like to be able to do in this situation? And situational demons. Do you see any of those situational demons at play? So now I'm going to highlight a couple of our findings. In the first scenario, finding a victim, in an earlier design session, we presented this as a possible solution. You can see the map is on the left-hand side. The green drone on the left-hand side has found a victim in the river. Imagery is shown in the panel on the right-hand side, and the firefighters have the options of confirming that this is a correct sighting, or that it's a false alarm, or request more imagery, or press a button to notify the commander. The firefighters rejected this as a design solution because they wanted the imagery to be much larger. They wanted the imagery of a candidate victim to take up as much of the screen as possible. And they told us that when we find a victim, we don't care about anything else at all. This was an interesting observation with respect to one of the situational demons of attentional tunneling, because the firefighters obviously were willing to embrace attentional tunneling when a victim was being rescued. The firefighters also had very much to say about autonomy. Now, this was the part of the system that was new and different from them, and they said this: the autonomous part is so new to us. And they had questions related to this. How do we know that the drone is recognizing a person as opposed to a first responder standing on the riverbank? And they wanted to know many things about why the drone was behaving as it was. This led to a number of very interesting design discussions about how best to portray autonomy and to explain autonomy to the firefighters during a mission. The firefighters also pushed the boundaries of the system. This was one of the excellent results of the participatory design. They imagined much more than we did. They, for example, told us that they wanted to have a part of the system that was designed specially for firefighters that were in a boat on the river. When a victim had been found, they wanted the coordinates of that victim to be pushed to a mobile app that the firefighters on the boat would have. As a result of the participatory design process, we identified many key issues in the user interface design, and we're currently implementing them in our new system. In addition to designing the next version of the drone response user interface, we're also enhancing our drone response architecture, which involves the central system, ground control system, and onboard computation. We're enhancing it to provide better support for the human-drone interactions that we explored and discovered in greater depth during this participatory design process. In conclusion, the drone response project introduces numerous human-computer interaction challenges. First and foremost, it represents a wicked design challenge. Secondly, it requires us to explore this new space of human-drone decision-making when multiple humans are interacting with multiple intelligent agents. Third, we need to consider all of these things while taking safety considerations such as providing situational awareness to the firefighters into account. And finally, we need to explore the societal and ethical implications of deploying semi-autonomous UAVs in emergency response scenarios. Thank you for listening. If you have any further questions, please feel free to visit our website, droneresponse.net, or send an email to me at janehuang@nd.edu. Thank you.